This video will go over question 4 in the Scholarship Entrance Exam 2019. It's called Bragg's Law, and we're asked first to state the necessary conditions for interference fringes to be produced by two sources of light at a distance d apart. Okay, so this is something that you need to know and need to remember, and the conditions, the first condition that we should always remember is that the two light sources must be coherent. What that basically means is that they have the same wavelength or frequency, either or, have same wavelength and a constant phase relationship. Okay, the second point that we could make here is that the distance that the separation needs to be comparable to the wavelength. The distance separating the sources must be comparable to the wavelength. And finally, the two wave sources must be sort of have a similar amplitude. The two sources produce waves of a similar amplitude. Otherwise, they wouldn't be able to cancel each other out. Okay, so that's a fairly complete answer to question number 1. The second one asks us to derive the equation for the conditions for constructive interference. And we know from our wave study that the condition for constructive interference is that the two waves are in phase, and therefore the path difference must be a whole number of wavelengths. So, in order to get a path difference of a whole number of wavelengths in this situation, we need to first recognize what in this diagram constitutes the path difference. And we can see that these two rays have traveled different distances. The bottom ray is longer than the top ray, and it's longer by this much. That distance, which we can call whatever A, B, C, that is the path difference. That's how much further the bottom ray has traveled than the top ray. So, based on our understanding of what's required for constructive interference, we know that the distance A, B, C must be equal to a whole number of wavelength for the two waves to interfere constructively at the detector. Okay, so let's write that down. So, for constructive interference, the path difference must be a whole number of wavelengths. M lambda. Okay, where m is 1, 2, 3, etc. Okay, in this situation, the path difference is the distance A, B, C. And we can see from the little triangle here, this triangle, that the distance AB and the distance BC are the same. AB is equal to BC, and we can see that actually this distance D here is the same as that distance in the middle, the hypotenuse of that right triangle. So AB must be equal to D sine theta. So the distance ABC is equal to 2 D sine theta, because AB is D sine theta and BC is also D sine theta. Okay, and so now we have an expression for the path difference. All that remains is to say just thus. Oh, do we have more space on the next page? Yes, we do. Thus, that I wrote this. I meant to write thus. Thus, for constructive interference, m lambda is equal to 2d sine theta, where m equals 1, 2, 3, etc. Okay, so now we've proved that part. Maybe just read the question one more time to make sure that we've fully answered it. Using your knowledge of the necessary conditions for constructive interference of the rays, derive Bragg's law. For constructive interference, the path difference must be a whole number of wavelengths m lambda. In this situation, the path difference is the distance ABC. Okay, I think that's a full answer. So, question 3 asks us now to make use of this. So, we're given that the shaded angle in the diagram is 29.2. The wavelength of the X-rays is 1.27. Calculate the interplanar distance d. So we have a third order X-ray diffraction maximum. So we have 3 times lambda is equal to 2 times d sine theta. Lambda is 1.27 times 10 to the minus 10 meters. And theta, well, theta we can get from this angle 29.2 probably. So let's go back to the diagram. Where are we? There we go. So we know that that's 29.2 degrees. So if that angle is 29.2 degrees, that means that this angle here is 180 minus 29.2, and this angle must be half of that. Sorry, it must be 180 minus half of that minus 90. So theta is equal to, we'll do this here. Oops, let's just get that back. There we go, and then back to full page view. There we go. So theta is equal to, apologies for the messy video, by the way. I'm just kind of learning how to use this stuff. So theta is equal to 180 minus, if I just scroll down a bit, minus 90. So that's, we're trying to get theta. The 3 angles in the triangle must be 180. We subtract that 90, and then we subtract half of that big angle there. Minus 180 minus 29.2 over 2. Okay, so that's equal to 180 minus 90 minus 180 over 2 is 90, and then plus 29.2 over 2. So here we can just see that all of this stuff goes away. So 180 minus 180 is 0. So it's just 29.2 over 2. So theta is just the shaded angle divided by 2. Okay, so let's go back down here to this. So theta is equal to 29.2 over 2, which is 14.6 degrees. So now we can just rearrange this equation. So D is going to be equal to 3 lambda over 2 sine theta, which is equal to 3 times 1.27 times 10 to the minus 10 over 2 times sine of 14.6. Okay, so let's work out what that is. 3 times 1.27 times 10 to the minus 10. Divided by 2 times 14.6 sine, close bracket, equals. So our answer then is that D is 1.92 times 10 to the minus 10. So heading back to here. Equals 1.92 times 10 to the minus 10 meters. Okay, so that is the interplanar separation. Did we need to add anything else? No, just calculate it. Okay, so moving on to the next question. Or should we write it in here as well? 1.92 times 10 to the minus 10. Alrighty. So, given the value of D calculated above, comment on why X-rays rather than visible light are used for diffraction experiments with crystals. Okay, so the first point that you need to be clear on is that X-rays have a much shorter wavelength. So X-rays have a much shorter wavelength than visible light. So X-rays are like 10 to the minus 10, while visible light is about 10 to the minus 7. Okay. The separation of the planes in the crystal is much smaller than the wavelength of visible light. So interference maxima will not be observable or observed using visible light. X-rays, however, have lambda approximately equal or in the same order of magnitude as D. Maybe we'll just write that. In the same order of magnitude as D. So interference maxima can be observed. Okay, so I think we've answered that question. I mean, we could look at that equation, m lambda equals d sine theta. If lambda is huge, then there won't be a theta below 90 degrees where we could actually observe a maximum. So we wouldn't be able to see any maxima. Okay. And that's the end of the question. So in the next video we'll have a look at this last LCR circuits question.